Welcome to our presentation. We did our research about an emerging technology known as fault-tolerant computing. As you are presenting, my name is Angel Manzi Gaju with my partner Miriam Uwingabiye. Some food for thought. Have you ever lost all your important data due to a hardware failure in your computer? Or have you ever experienced the infamous blue screen of death and felt helpless as your computer crashed? Computers are inherently prone to failure, but in the world of fault tolerant computing, experts are working to minimize the impact of these failures and ensure that the critical systems remain operational even in the face of hardware and software failures. Heading to our table of contents, we'll talk about the introduction to fault-tolerant computing, the methodology we used, we'll continue with our discussion, and give an overall analysis of the topic. Our introduction. Fault-tolerant computing refers to the design and implementation of computer systems that are able to continue operating even when one or more components fail. This goal of fault tolerance is to ensure that the system remains available and can continue to function as intended despite the failure of one or more components. Some of the examples of real-life situations that involve fault-tolerant computing, one of them is how it is very vital in hospitals to ensure patients' safety. It is also important in aviation for backup mechanism. It's also important for maintenance of power grid, and it also helps to avoid power outages. The final one is that it helps in the finance industry to maintain the reliability of financial transactions. Heading to the methodology. Even after so many testing methods, there is still the potential for system failure. Practically, no system can be completely error-free. As a result, systems are constructed so that in the event of error availability and failure, the system accomplishes the work correctly and provides the correct output. Any system is made up of two components, which is the hardware and software. For the software, it's designed to ensure that software systems continue to function reliably even in the event of component failures or malfunctions. And for the hardware, it is designed to prevent system failures and ensure continuous operations in the event of hardware faults or failures. To elaborate about the hardware fault tolerance techniques, we'll start with the built-in self-test, which is the hardware fault tolerance technique that autonomously executes self-tests as predetermined intervals to detect and replace fault paths. The second one is the triple modular redundancy, which produces the redundant clones of a component that run concurrently and use a voting method to ensure the proper results in chosen. The last one is the circuit breaker, which is a circuit design that monitors a system's health and breaks the circuit to prevent further damage, frequently used in the distributed systems. For the software fault tolerance techniques, we'll start with the end version programming, which produces multiple independent versions of the software system that run concurrently to detect and rectify flaws. The second one is the recovery blocks, which divide the system into smaller independent components that detect and recover from errors. Another one is the checkpointing and rollback recovery, which sets the system's test at checkpoints to enable a quick recovery from faults. The fourth one is the failure oblivious computing, which allows programs to continue running despite errors, improving the system's availability and reliability. The last one is the recovery shepherding, which allows programs to recover from faults while continuing to run normally, reducing downtime and maintaining the user experience. Resuming with our discussion, we'll talk about the advantages of fault-tolerant computing. The first advantage is scalability. The second one is cost effectiveness, increased reliability. Going to the disadvantages, we have its complexity in design, how costly it is, and the false sense of security. Heading to the challenges, we identified the potential faults, reducing fault detection time, and managing system complexity. Ending with the future work, or what we expect in the future that is coming, we'll see the virtualization, managing system complexity, and machine learning for fault detection and prediction. For the summary, for the implication of this project, we found that it's improved system reliability, increased data integrity, increased system performance, and also high upfront costs. For the conclusion part, fault-tolerant computing is crucial in the digital world for high availability and reliability of critical applications. Building fault-tolerant systems can increase system complexity and require additional hardware and software components, making design and development more challenging and costly. Despite the costs, the long-term benefits of fault-tolerant computing, such as improved system reliability and data integrity, make it an essential consideration for organizations. Continued research and development of fault-tolerant computing is critical to ensure that critical applications and systems remain operational in the face of hardware or software failure. These are our references that we used, and thank you so much for our presentation.